Okay, we're recording. Lesson 3.4, it's our first day talking about the second derivative and its usefulness, and that will bring in the discussion about concavity. So we're going to find intervals of concave up and concave down. We're also going to identify points that are points of inflection. And then on the next day when we work on this lesson, we'll look at how else the second derivative test may be used. You're going to find some similarities with what we have done with first derivative tests coming into these second derivative tests. So just a little bit of review. Concave up. One easy way to remember that is it's up like a cup. If it holds water, if your function would hold water, then it's concave up. For example, I have concave up in this region, up like a cup. Otherwise, the other option we could have is concave down like a frown. And in this region, I would be concave down. When I'm going along this curve and I'm concave down, there has to be at least some point where things switch over and I change the bending. That point where it changes bend is known as an inflection point. So these here are inflection points that we've got arrows to. So this will all become a little bit more clear as we go through it. Just as a review, first derivative locates extrema for us. It also indicates the direction of the function, whether it's increasing or decreasing. Increasing or decreasing. And the second derivative is going to locate points of inflection and help us note concavity of our function. So there are three different ways that we could have a function with a first derivative that is positive. In other words, we've got an increasing function, an increasing f of x. Draw three different ways that this might appear. Let's do a simple one first. It could just be linear, a nice linear function that is increasing. So my f prime would be greater than 0. My f double prime, well, what does f double prime represent? Well, f double prime really is the derivative of the derivative, isn't it? So it's the rate of change of the rate of change. So how is the rate of change along this linear function changing? Well, if I drew in tangent lines, do those slopes ever change on my tangent lines? No, they do not. This would be a second derivative that's equal to 0. The function f of x increases at a constant rate. Thus, our second derivative is equal to 0. Another curve that could happen that's increasing is one that does that. Here we have f prime greater than 0. I've got an increasing function. And the second derivative, well, draw in. Maybe pick 3 spots here, and let's look at the tangent lines. Well, this one is positive, this one's getting more steep, and this one's even steeper still. It's even, I'm going to put triple positive on it, it's getting really steep. So what's happening to the slope of these tangent lines? Well, the slope of the tangent lines are increasing. So we can say f of x is increasing at an increasing rate. Third style of function could be one that is curved like this. And it's still increasing. My y values are getting bigger as I move. As my x values increase, so do my y values, right? So this would be an increasing function. F prime, I would note, is bigger than 0. And f double prime, well, draw in those tangent lines again. This time we're going to be on the upside, the above side of our curve. It's positive and more steeply positive here than here than here. So it's actually kind of slowing down. These will have slopes that are decreasing. The slope of the tangent line is decreasing. So I got f of x is an increasing function, but it's increasing at a decreasing rate, which causes it to start slowing down the bend. Easy way to remember some of these: concave up like a cup. Well, with concave up, our second derivative will be positive, Let's put positive eyes in and put a smile. That's a concave up curve, isn't it? Concave down will be when our second derivative is less than 0. So I've got negative second derivative with a frown. Zero concavity. Zero concavity. That means we've got 0 for our second derivative. This constant idea that we showed up here in example 1. And let's throw some eyes in there. The poor guy, he's just flat, isn't he? A linear function will have 0 concavity. Another thing to look at, determine the signs of f and f double prime for each of the curved segments below. So kind of taken a circle, blocked off some spots on it, and came up with different shapes of curves. If you want to, go ahead and draw some tangent lines on here. Is the direction of the tangent line positive or negative? Is the slope of the slope of the tangent lines are positive, aren't they? So first derivative is 0 or greater than 0. Second derivative, are they getting more steep or less steep for their slope of the tangents? Well, here we've got, slightly positive and even less positive there. So the second derivative is decreasing. It would be negative. On this one, if I drew in tangent lines, I am negative, right? And then getting more negative and even still more negative. So the function is decreasing. The y values are going down, aren't they, as my points, as I travel along my curve. And the second derivative is negative. It's less than 0. So it's decreasing at a decreasing rate. F prime here, okay, if I take this point and compare it to this point, it is a decreasing function. You could also connect, a secant line. You can see how the y values are getting less. And the second derivative, well, throw in our slopes. This is pretty sharply negative, a little less negative, and now it's getting softer down here. So maybe triple, double, and single. And that means that it's getting less negative, which means that the rate of change is increasing. So we've got an f double prime that will be positive for this shape, where it's a decreasing function that's concave up. F prime on this one, moving left to right, the function is increasing. So we have f prime being greater than 0. If I look at these tangent lines, positive slopes, getting more positive, getting more sharply positive, the rate of change of the tangent lines is increasing. So we get second derivative positive. Test for concavity. Let f be a function whose second derivative exists on the open interval. Then if f double prime, second derivative for all x in the intervals, exists, the graph will be concave up. We've been talking about this. F double prime less than 0, the graph will be concave down. Points of inflection. Here is the definition of a point of inflection. If c comma f of c, our y value, is a point of inflection on the graph of f, then either I have the second derivative equal to 0, or the second derivative does not exist at that point C. These are sort of like our critical values, right? It seems almost the same as, if an extrema occurs, it will occur either at f prime of C equal to 0 or f prime of C not existing. So very, very similar in its approach here. We talked about this in the beginning. There's this curve here. The point at which our concavity switches is going to give us an inflection point. So we're going to walk through a problem, find the points of inflection and justify your answer, discuss the concavity of the graph of the function. So find the points of inflection. Well, the first thing I think I'm going to do, because I know I need to do a second derivative, because second derivatives give me points of inflection, is I'm going to simplify out, I'm going to distribute through and make this a little bit easier function to deal with. So let's send the x cubed through. Next, f prime of x. Well, a nice easy one, 4x cubed minus 12x squared. I could sit and pause and come up with a sign chart for first derivative, look for my critical points, and talk about extrema. But our goal today is really let's focus on points of inflection. So hop straight into second derivative. That'll give me 12x squared minus 12x. And the previous page talked about points of inflection occur either at second derivative equal to 0 or does not exist. We also would have to watch for those points of discontinuity, and which brings me back to we should have looked at our domain, which was all reals. So we don't have any points of discontinuity for the original function. F double prime is also a polynomial. Its function is good over all real numbers as well. So I won't have any points of discontinuity. So we're going after possible. Now this is interesting, isn't it? These are possible points of inflection. I'm saying possible because they are not points of inflection if I don't have concavity changing. All right, so we're going to take our second derivative and set it equal to 0. We also said we should look at where it's DNE, but we know on this particular one, this is going to end up being a blank. Now, let's factor that. We'll pull out a 12 and an x, and that's going to leave us an x minus 1. Set it equal to 0, and I have 2 possible points of inflection. And one of them occurs at 0 and the other occurs at 1. Now, what I'm interested in is the sign around this. So we go into a second derivative sign chart. And it's going to be created just the same way we did our first derivative sign chart. Number line, place our values on the number lines, put 0 up above and the 1 up above. Those are my x values. I'm going to indicate I'm doing a second derivative, so f double prime. And once again, come in with some test values. My fully factored form of the equation was this, so that's what I'm going to be referring back to. To the left of 0, I'm going to call it negative 1. I'm going to spot one at positive half, and then I'm going to spot another one here at 2. So I need to examine the second derivative at negative 1. I need to examine the second derivative at a half, and I need to examine the second derivative at 2. What I'm looking for is the sign. So I put in negative 1, I'm going to have a negative times a negative, giving us a positive region. For 1/2, we put in 1/2, and we will have a positive followed by a negative, giving us a negative region. And put in 2, and it'll be positive, positive, yielding a positive outcome. This will be up like a cup, down like a frown, up like a cup. So I can indicate my concavity here by doing just simple little curves. Now, how can we classify 0 and 1? Well, they are points of inflection if we have sign changes. So this 0 is a point of inflection. Occurring when x is 0, and I have a point of inflection at x equals 1. Now, point kind of implies that it's a coordinate pair, so we could find the y value to it. I'm just not going to do it today. Stating this, f of x has a point of inflection at x equals 0. Why? Well, because f double prime changes, just like extrema, we've got to have the derivative changing. So it changes from How did it change? It went from positive to negative. Went from positive to negative. Where did it change? It changed at x equals 0. I can repeat the same thing. F of x has a point of inflection at x equals 1 because f double prime changes. How does it change? It changes from, this time it was going from negative to positive. Look back at our sign chart. We went from negative to positive at x equals 1. We could talk about concavity. F of x is concave up on the interval negative infinity to, we were concave up. I got to see my sign chart here. Concave up from negative infinity to 0, and then also from 1 to infinity. So I'll get those two. Negative infinity to 0. Union that with 1 to infinity because f double prime was greater than 0. And then you could repeat f of x is concave down on the interval that is in the middle from 0 to 2. Ooh, did I do something wrong? I had 24 on my other. I think we're okay. On I sure did. I just noticed I was looking at my notes. I'm sorry, I messed that up. Put 24 there, guys. 24, which leads us to a 2. Go fix these up. And a 2 here. So then we would have tested 3. And I think we'll be okay. Tested 3 there. And now, where do we got? Inflection point at 2, at 2. I'm not going to redo the video because that would take forever for me to redo this. And 2, and we're back square, aren't we? So sorry about that. F of x is concave down on that intermediate interval between 0 and 2 because f double prime turned out to be negative. Got it? Finally, we have the last one. Find the points of inflection and discuss concavity of the graph. So domain, well, there's domain issues, right? The domain of f, we would not want x to be negative 1/2. And we'd have to do quotient rule, and then that would get us a first derivative. Then I'd have to do quotient rule again, and that would get a second derivative. But I thought, let's just kind of pick up on second derivative and work from there. So think of it as my gift to you guys. So here we go. We got f double prime is equal to this. So how do I find my possible points of inflection? I look for places where the first derivative is equal to 0, or where the second derivative is equal to 0, or the second derivative is d and e. Okay, on the top, the only thing we've got is -6. Will -6 ever equal 0? Nope. So we have none coming from here. How about the second one? Well, let's take this and set it equal to 0, this being the denominator. And solving that, we have one possible point of inflection. But in fact, I know it's not a point of inflection because this is not part of the domain, right? So I can have regions of concavity changing around it. I just won't call x equals -1/2 a point of inflection value. So not part of domain. So when we go into our sign chart, which we're going to do next, let's make our sign chart. For the second derivative, x on top, f double prime is going to reside below. I'm at the marker of -1/2. Choose a number to the left of it. Okay, I'll choose -1. Choose a number to the right of it. I'll choose 0. Look at what its value will be. And I'm going to go back to f double prime right there. So f double prime of -1. Well, the top will be negative, and the bottom, I go negative 1, that'll be negative 2, plus a 1 will be negative 1 cubed. That will stay negative, so I get a positive region right here. And then if I do f double prime of 0, a nicer one to calculate, I have negative on top, positive on bottom, negative overall. And I'm just going to kind of hide that so I know that I don't have a point of inflection. What I do have is concave up before this point of discontinuity, or region of discontinuity, vertical asymptote, and a negative, so concave down. Here is a graph. You can see concave up. Here's our asymptote at negative 1/2, and then we get this region of concave down on this side, concave up on the left. And then we could go in and write out the particular things, but you've got an example from the previous one. I think what we'll do, we'll come back to class and work on example 5 today together, so that'll make a nice point where we can recap again. So, homework, please give these a try. There are 6 problems, and just follow our notes. Have a great day.